write a Raytracer in Python and it runs slowly. I write it in Rust and it runs slowly. Automize it, make it run multi-threaded and it runs slowly. I resign and buy a new CPU and it runs slowly. Anyway, I'm going to try to attempt to build CPU Raytracer smooth as a video game, but it might not be easy. Foreshadowing. But don't worry, it's exactly as complicated as it sounds. Story time. I'm Shane, but I have to tell you a secret. I started this project in Python. Please don't laugh at me in the comments below. I suffered a lot. Python lets you prototype fast, but in the end, you end up spending way more time optimizing, and the performance gains are usually pretty disappointing. For pixel by pixel rendering, it's just too slow. No native fast multiprocessing support, and the GIL kills parallelism. So I looked for something faster. Something much better. Rust. The language of performance and safety. No garbage collection, no GIL, and zero runtime overhead. With Ryzen, I leverage CPU multithreading effortlessly, making my Raytracer scalable and snappy. Features you ask? We will implement dynamic lighting, shadows, textures, all without relying on external 3D engines. No classes, no garbage collections, no animals harmed. Just pure, efficient Rust code. But before we dive into the code, there's just one thing you need to know. Our simplified ray tracing algorithm is built around a core principle: shoot exactly one primary ray per pixel. In the first example, we cast a ray towards a reflective mirror ball. The ball reflects the ray towards a wall, simulating specular reflection. When the ray intersects the wall, we sample its surface color. From that point, we shoot a secondary ray towards a light source, representing direct lighting. If the path of the light is unobstructed, the pixel color is bright. If any object blocks the light, the pixel appears dark, creating a shadow. This approach captures basic reflections and shadows with minimal complexity, making it a solid foundation for more advanced effects. First, we set up a window to host all the graphics. The core processing occurs within the event loop. During this phase, we handle key bindings, display statistics such as frames per second, and camera position, and initialize the rendering of each frame. Within each frame, we calculate the movements of all objects and populate the image buffer. This image buffer is generated by casting rays from the camera, one ray per pixel. A single ray travels through space until it encounters a wall or object. In our example, only objects are reflective. When the ray hits an object, it bounces off by reflecting against the surface's normal vector. The reflection is calculated using this formula. Here, V is the incoming ray direction, N is the surface normal at the point of contact, and V dot product N is the dot product between the two vectors. This formula ensures that the reflected ray follows the correct angle, bouncing off surfaces realistically. In the main RS file, we initialize a piston window which serves as a canvas for all rendering operations. Within this setup, we load necessary assets such as textures and define constant values used throughout the program. The core of the rendering process is managed by an event loop that also handles user input like key presses. Inside the Draw2D method, we render on-screen metrics and display the complete scene from an image buffer, pixel by pixel. This image buffer is generated within the compute1tick method, which updates the scene's objects such as mirror balls or a player, and reconstructs the image buffer accordingly. To generate a scene, we create an empty image buffer and iterate over each pixel coordinate x, y. For each pixel, we compute the starting position of a camera ray that projects into the scene. The find_wall_color method is then called for each ray, simulating its traversal through the scene. The ray advances step by step, checking for intersections with walls or objects. If a wall is intersected, we sample its color and spawn a secondary ray to determine the visibility of light sources, aiding in shadow calculation. If an object is hit, the ray is reflected and bounced against the object's normal vector, simulating realistic lighting effects. When calculating shadows, the compute shadow method traces a ray towards the light source to determine whether the point is in shadow or illuminated. And that's it. That is the naive implementation of Raytracer. Let's take a look how fast it is. Yes, that's not optimal. We have a lot to improve. So let's do it. The first optimization we will implement is boundary checking. If the array exits the defined word boundaries, we can immediately terminate the process, avoiding costly computations such as collision detection. And here we have it. The rendering is almost 3 times faster, but it's still not enough. So let's continue. The second optimization we will introduce is Manhattan distance filter for objects on the screen. By calculating the Manhattan distance, which involves checking one axis at a time between the ray's origin and each object, we can quickly determine if an object is potentially within reach. If the distance exceeds a certain threshold, we can skip detailed collision checks for that object, further improving performance. It's a double the speed, but I think we can do better. The third optimization is fast ray stepping. Since the objects are large, when a collision is detected, we can step back a bit along the ray and refine the collision point precisely. This way, we skip checking every small step and only do detailed calculations when we are close to an object, saving processing time. Let's check the results, and it is double the frames per second for fast travel towards walls and additional 20% when fast traveling towards light source. Now, to make the rendering even faster, we can process multiple pixels at once using Ryzen. When we replace enumerate with par enumerate, which runs the loop in parallel, this allows many pixels to be processed at the same time, speeding up the overall process. But only if your CPU has more than one core, like AMD Athlon 64X2 or Pentium D, or probably anything younger than 20 years. By enabling multiprocessing, we manage to multiply our frames per second by more than 3 times on AMD Ryzen 5600X. And because I made these benchmarks more than 1 year ago, let's take a look how current CPU would handle this load. Now go and try it for yourself, have fun and make it better. Link for the source code is in the description below. Thank you for watching.